Prova, prova. Prova.
Okay.
So welcome to this afternoon session. It's a great pleasure to introduce Professor Andrea Mondino from the University of Oxford. So Andrea's research interest lies at the interface between analysis and geometry. Andrea got his PhD in Sissa with Professor Malchiodi. Then he was postdoc at the Scuola Normale in Pisa, TTH, and at MSRI in Berkeley, I guess. And later he had positions at University of Zurich, and then in Warwick, and now he's in Oxford. He was awarded several prizes for his research activity, like Bartolozzi Prize, the Gioacchino Iapichino Prize, and recently the Whitehead Prize from the London Mathematical Society. He is the recipient of an ERC starting grant. And today we will speak about geometry life. Smooth and no smooth aspects of rigid curvature lower bounds.
Can you hear me? Good. All right. So first of all, I wish to thank David for the introduction and for the invitation. It's a great pleasure for me to be here today with you. And I wish to congratulate the organizers for the excellent organization and for the idea of organizing this forum for young researchers and PhD students. I think it's a really very good idea, and I encourage you to take the best out of these 2 days to make connection with people of your field and of your age. It's out of your group at your university. I think it's a very, very good opportunity. All right, so let me start. Okay, so to change slide is this one. All right, so let me start with something that we all know very well from the second year of university, which is the Gaussian curvature of a two-dimensional surface. So we start with a two-dimensional surface, sigma. Two-dimensional surface sigma, endowed with a Riemannian metric G. So every tangent space is endowed with a scalar product. We have the Levi-Civita connection, nabla. So this is a very good place for this name. And once we have the Levi-Civita connection, we can speak about the Gaussian curvature. So let me recall the definition. So we fix a point P, a coordinate basis, Ex, Ey, a basis of the tangent space. And the Gaussian curvature at the point P is defined as follows. So we consider the first vector Ex, we consider the covariant derivative with respect to Ey, Ex, and we switch the order and the sign. So here we get another tangent vector, and we take the scalar product with the second tangent vector. Okay, so this gives me a scalar, and then we normalize it with the determinant of the metric to make it scale invariant, to make it invariant under change of coordinates. So it is well known that when the surface sigma is isometrically immersed in R3, then the Gaussian curvature has probably the more familiar form as the product of the principal curvatures, and this is the famous theorem egregium of Gauss, which is nothing but the Jacobian of the Gauss matrix. Okay, but this we know all from second year of the university. And now it is good to have in mind some examples for the next development. So the classical, the standard example of something of zero curvature is the Euclidean plane R2. Indeed, if you have R2, then you can just switch the derivative by the Schwarz lemma, and so this is zero. If instead you have a sphere of radius 1, then it has Gaussian curvature equal to 1. And if you have a larger sphere, this larger sphere will have lower curvature. So the larger the radius, the lower the curvature. And instead, the standard example of something with negative curvature is the hyperbolic plane, or the Poincare model, or the half space. Okay, so this is surfaces. Now, how to define curvature in higher dimensions? So if we have an n-dimensional space, how one can define curvature? So this can be done by playing with the Gaussian curvature. Let me recall the basic definitions. So we have an n-dimensional manifold with a Riemannian metric G. We fix a point P, and now I want to tell you what is the curvature on a plane. So I fix a two-dimensional plane pi in the tangent space at P, which is spanned by two vectors, say E1, E2. And then, in order to define the curvature of this plane, what I consider is, I have this plane here, and I consider all the geodesics which I obtain by, which are spanned by this plane. So I take all the velocities which are tangent to this plane, and I shoot the geodesic for a very short time. Okay, this is nothing but the exponential map at the point P of the ball of radius epsilon integrated with the plane pi. This is the surface which is obtained by considering all the geodesics starting at the point and tangent at time 0 to the plane pi, up to a short length epsilon. What is well known is that for epsilon small enough, this union of all the geodesics span a smooth two-dimensional surface, and then one can define the sectional curvature at this plane as the Gaussian curvature of the surface at the point P. Okay, so we can define the sectional curvature just by knowing the Gaussian curvature from second year of university. Okay, and then once we know the sectional curvature, we can define the Ricci curvature by taking roughly the trace of the curvature. How to do it precisely? So the Ricci curvature takes a vector, a tangent vector V, and gives me a number. So it's the Ricci vector. And it will be clear in a moment why I use this notation. So take a vector V which is non-zero, and normalize it to have it to have length 1, and then complete it to an orthonormal basis. So you have an n-dimensional space, so you're going to have an a base with n elements, E1, E2, En minus 1, and the vector normalized. Okay. Now what you do is you take the planes which are spanned by the vector and all the other elements of the base. So take first the vector V and the vector E1, and you have the first sectional curve, the first sectional curvature. Then you sum to it the sectional curvature of vector E2, second plane, and you go on. So you have n minus 1 planes. You sum all them up, and you get the Ricci curvature. And then for normalization, you multiply what you get by the norm of V squared. Okay. All right. And by definition, if the vector V is equal to 0, you say that the Ricci curvature is equal to 0. Okay. It turns out that if you do that, you can define a quadratic form. So the Ricci as this dV is because it is a quadratic form on V, which has several interesting properties. Okay, so for what comes next, it is useful to understand what does it mean to have lower bounds on the Ricci or on the sectional curvature. Okay, so what does it mean to have a lower bound on the sectional curvature? So given a constant k, we say that the sectional curvature is bounded below by the constant k if for every point and every two-dimensional plane pi, the sectional curvature at the plane pi at the point P is bigger or equal than k. Okay, this is easy. Okay, now what about the Ricci curvature? So the Ricci tensor is a quadratic form. So what does it mean that a quadratic form is bigger than a constant? Okay, so basically it means that all its eigenvalues are bigger than the constant. So more precisely, we say that the Ricci tensor is bigger than the constant k if the quadratic form that you obtain by taking Ricci minus constant time the metric tensor G is non-negative definite. This amounts to say that all the eigenvalues of the Ricci are bigger or equal than k. Okay, now again some examples now in dimension n. Of course, the n-dimensional Euclidean space has sectional curvature equal to 0, and then Ricci equal to 0 just because we are summing up 0. Now, the n-dimensional round sphere of radius 1 is sectional curvature equal to 1, and then since we are summing up n-1 planes, the reach is n-1. The n-dimensional hyperbolic space is sectional curvature equal to -1, and the reach curvature equal to -n-1. And these three cases are very important to keep in mind because they form the models when you want to study comparison geometry. So when you have a lower bound on the Ricci curvature, if the lower bound is 0, then your model space is the Euclidean space. If the lower bound is positive, your model space is the round sphere. If the lower bound is negative, your model space is typically parabolic space. So it is very useful to have in mind these model spaces. Okay. Now, a beautiful branch of differential geometry is the so-called comparison geometry, which roughly amounts to answer the following question. If I'm given an n-dimensional smooth Riemann manifold, and if I assume some upper or lower bounds on some curvature, Ricci or sectional, the question is, what can I say about the analysis for the geometry on the manifold, just by knowing something, just by knowing bounds on the curvature? So what is well known is that the upper or lower bounds on the sectional curvature are strong assumptions with strong implications. Okay? For instance, both at the level of topology and at the level of geometry. So for instance, a beautiful theorem due to Cartan and Adamar is that if you know that the manifold has a non-positive sectional curvature, then its universal cover is diffeomorphic to Rn. Okay? So this implies, for instance, that if you know that manifold has non-negative, has non-positive sectional curvature, all the topological information of the manifold are encoded in the fundamental group. Right? Because then you can recover it just by the universal cover. Okay, and instead, and another beautiful result in sectional curvature comparison is the Topogonov triangle comparison theorem, which basically says the following: we are given a manifold M, and I take any 3 points, P1, P2, P3 in M. So let's say here P1, P2, P3. Okay. Then consider in R2 points P1 bar, P2 bar, and P3 bar, such that the distance between the points in R2 is equal to the distance in the manifold M, say Mg, of the points Pi, Pj. Okay, so I have these 3 points in R3 with the same relative distance. Then I consider a geodesic which connects P2 to P3, so let's call it gamma. Gamma, say it's parameterized on 0, 1 with values into M, which is a length minimizing geodesic parameterized by arc length, and I do the same here in R2. So, and I have my gamma bar is the parameterized segment from P1, from P2 to P3. Okay, so I have these 3 points and these 2 curves. Okay, now let's consider a. Can you see it? It's a. Okay. Okay, good. Okay, so I consider an intermediate point of the geodesic gamma t, and I do the same, and I consider the corresponding point, the gamma bar t of the segment gamma bar. Okay, and now I am interested in comparing the length of this segment with the length of the corresponding segment in R2. Okay, and now it turns out, and this is the beautiful Topogonov triangle comparison, Topogonov theorem, says that your manifold Mg has a
portion of blackboard is not seen.
okay, all right. my same words. So the Topogonov comparison theorem says that your manifold has a sectional curvature bigger or equal than 0 if and only if the distance from the point P1 to gamma t is bigger or equal than the distance in the comparison space between P1 bar and gamma bar t. Okay, so apart from, okay, so the idea is that I have a smooth manifold and I want to characterize lower bounds on the sectional curvature just by looking at distances and triangles. So apart from the precise statement that probably is not so easy to get in a short explanation in a short space, what I want to stress of this theorem is that you are characterizing lower bounds on the sectional curvature just in terms of distances and geodesics. This is the key point. Okay. Why it's a key point? Because in order to define the sectional curvature, if you go back to the definition of Gaussian curvature, we are taking iterative derivatives, and you need smoothness of the metric G in order to do that. In more precise, you can check that you need that the metric G is C2. Okay. So this left-hand side uses the C2 structure of your manifold, but this right-hand side of this theorem is just using the metric structure of your manifold. And then it was the starting point of a beautiful field called Alexandrov geometry. Indeed, the idea of Alexandrov was to take as definition of non-negative sectional curvature for a metric space this right-hand side of the theorem. Okay, so once you have a smooth characterization which involves just the metric, you can take this characterization as a definition in the non-smooth world. All right. Okay. This was about the sectional curvature, and then what about Ricci curvature? So we have seen that both upper or lower bounds on the sectional curvature are very strong. Well, what about Ricci? So what turns out is that what it turns out is that upper bounds on the Ricci curvature are very weak assumptions for getting conclusions. For instance, it was proved by Locamp that if you take any compact manifold of dimension at least 3, then it carries a metric of negative Ricci curvature. Okay, so while by Cartan-Adamar theorem, if we know that the sectional curvature is negative, we have some topological information. From the Ricci, that's not the case, because just any manifold will carry a metric with negative Ricci. Okay, so what about instead lower bounds on the Ricci? Well, it turns out that lower bounds on the Ricci curvature give a natural framework for studying comparison geometry. There are plenty of results. Let me just mention a few, and actually one. So a very important result is the Bishop-Gromov volume comparison that I mentioned in a simplified setting. So assume that your manifold has a non-negative Ricci curvature, then one can control the volume of the ball of radius r with the volume of the ball of radius r in the Euclidean space. Okay, so and actually you also have a monotonicity. Okay, then if you have lower bounds on the Ricci, you can control the Laplacian of the distance function. There are some beautiful splitting results. You can control the heat flow by the Liao inequalities. You can control the isoperimetry by the Levi-Gromov inequality, and many other results. Okay, so but all of that was about the smooth world. Now let's go to the non-smooth world gently. So the motivation for doing that comes from Gromov, who in the 80s introduced a notion of convergence for Riemannian manifolds, now known as Gromov-Hausdorff convergence. So if you know, it is a generalization of the Hausdorff convergence of compact sets inside a metric space. Here, instead of having a fixed metric space and having the Hausdorff convergence of compact sets, you have instead the convergence of metric spaces themselves. And the idea is to embed isometrically your metric spaces into a common ambient metric space, and take the Hausdorff distance there, and take then the infimum among all the possible isometric embeddings. Okay, but apart from the precise definition, what I would like to stress is that this Gromov-Hausdorff convergence is a zero-order convergence on the distance function. So in a first approximation, you can think of it as a uniform convergence of the distance function on the on the product x times x. Okay, it is actually weaker than that, but as a first approximation, you can think of it. Okay, so but it is so you have a way to speak of convergence of metric spaces or of Riemannian manifolds. And the key observation by Gromov is that if you have a sequence of Riemannian manifolds with lower bounds on the Ricci curvature and fixed dimension, then this sequence is pre-compact under this notion of convergence. Okay, so you have the pre-compactness theorem, and then you are going to get some limit spaces, and these limit spaces are going to be in general not anymore smooth Riemannian manifolds, but they can have singularities. So the first example is the one of a cone. So if you have a cone, then you can see it as a limit of smooth manifolds like that. You can desingularize a cone, but the tip is going to be a singular point. Okay, and you can play and produce say spaces which much wider singularities. Even say on a dense set, you can have singular points on a dense set, and so on. Okay, and the natural question is raised by Gromov is, what can we say about the compactification of the space of Riemannian manifold with lower bound on the Ricci curvature? And the hope is that the knowledge of the compactification can be useful also to establish new properties for the smooth manifold themselves. Okay, so this program was pushed violently by Chigar and Kolding in a series of 3 beautiful papers at the end of the 90s. I don't have time to discuss their beautiful results. And then it was pushed even further recently by Kolding-Naber and Chigar, Zhang, and Naber in 2 papers at Atlas. I will discuss some of the related content later. Now I will skip it. But what I want to stress is that what Chigar, Kolding, and Kolding-Naber, and Chigar, Zhang, Naber were interested in was on the studying the structure of the limit spaces. Okay, so what it was understood fairly quickly was that these limit spaces are non-smooth, but how non-smooth can they be? So the fact that they can be approximated by smooth Riemann manifolds, what information on their structure is giving us? Okay, what it was, for instance, understood is that the tangent spaces almost everywhere are Euclidean. So at least at an infinitesimal level, the limit space is regular. Okay. And then many more results were obtained. Okay, but what I want to stress here is that this approach to Ricci curvature is very powerful if one is interested in studying the structure of the limit spaces, but is not answering the more fundamental level, the question at a more fundamental level, which is what does it mean for a non-smooth space to have a lower bound on the Ricci curvature? Because here we are just considering those non-smooth spaces which arise as limits of smooth objects. So only those spaces which can be approximated by smooth objects. Okay. While for the sectional curvature, we had a precise picture thanks to the topogon of triangle comparison. Okay. So the goal of the first part of the talk is to answer this question. And since I see many experts in the audience of geometric measure theory, it is very much in the same spirit of more classical geometric measure theory. So in classical geometric measure theory, one studies C1 submanifolds, say with a bound on the area. One has a natural notion of convergence of C1 submanifolds, which gives good precompactness properties. Usually, say weak convergence of measures. And then if one considers a sequence of C1 submanifold which converge with respect to this weak convergence, one obtains in the limit some non-smooth object. Okay? And then in order to have a theory which encompasses C1 submanifolds by allowing some singularities, and one introduces, for instance, the class of set of finite perimeter or currents or varifolds. And what is the big advantage of these classes is that they are closed under the notion of weak convergence. And then one proves theorems in this enlarged class and tries to go back to the smooth world. And here we are going to do, and the goal here is very similar in speed. We want to enlarge the class of smooth Riemann manifolds by allowing, say, weak Riemann manifolds, say, manifold possibly with the singularities, in a more general class which is compact now with respect to this notion of with respect to this weak notion of convergence, and then hopefully try to go back and see something interesting on the smooth world. Okay, so the preliminary observation is in which class we want to find this non-smooth object. So when we are in an ambient space like in classical GMT, we have an ambient space, and our weak objects are some special classes of measures in some way. So here, where can we look for these non-smooth objects? So for sectional curvature bounds, the good non-smooth objects to look at are metric spaces with a good notion of geodesics, and these are the Alexandrov spaces. And that's because of this theorem by Topogonov that I mentioned before. And why this is the case is because we were able to characterize sectional curvature just in terms of the distance function. Okay? If now you look at all the important comparison theorems for the rigid curvature, you will see that they involve the interplay between distance and volumes. For instance, in the Bishop-Gromov volume comparison, this is manifest because it is a control on the volume of metric balls. So you need a distance to define a metric ball, and you need a measure to define its volume. Okay, and actually this is a deep fact, the fact that you need to consider both distance and measure, and that's because basically rigid curvature is not just a property of length themselves, but it is a property of length and volumes, and so one needs to fix a reference volume measure, and the natural setting is given by metric measure spaces. So a metric space endowed with a reference volume measure. Okay, so now the setting from now on is going to be given by metric measure spaces. So for simplicity, I will consider the case when the metric space is compact. So XD is a compact metric space, and I'm going to endow it with a finite non-negative Borel measure M, which is going to play the role of reference volume measure. But actually, all that I'm going to say holds more generally for a complete and separable metric space endowed with a sigma finite volume measure. Just it is more complicated to formulate, and the notation becomes a bit heavier. So that's why I simplify a little bit the setting. So given a compact metric space, we are interested in the space of probability measures, which are non-negative Borel measures with mass equal to 1. And if you have followed the lecture yesterday by Figalli, you know the optimal transport distance. So there's a natural way of defining the distance between two measures using optimal transport. When here I'm fixing the cost, which is the distance squared, which is the following. I fix two measures, mu1 and mu2, and I want to define its their distance. Okay, so what one does is one considers all the probability measures in the product x times x, such that the push forward on the first factor is the first measure, and the push forward on the second factor is the second measure. So this gamma should be seen as a way of transporting the measure mu1 into the measure mu2. Okay, and given such a gamma, I we consider the cost of this transport, which is the integral of the distance squared with respect to this transport gamma. And then we take the infimum among all the possible ways we can transport mu1 into mu2 using such a gamma. Okay? One can prove that this gives a distance, and that this distance inherits a lot of good properties from the underlying metric space. For instance, if the metric space X was a geodesic space, then the Bastien space is geodesic itself. Geodesic means that any 2 points can be joined by a line-minimizing geodesic. Okay, so this is the optimal transport in a metric space. Now, for simplicity of notation, from now on, I will just assume that all the measures are absolutely continuous with respect to the reference volume measure. Okay, so from now on, all the measures mu are going to be a multiple of the reference volume measure m with respect to a weight of total mass equal to 1. Simplify the notation. Okay, and on the space of probability measures, I will consider some functionals called entropy functionals. Okay, so these are some deep connections with the first talk of this morning in statistical mechanics. So, so for n equal to infinity, the entropy functional is the Boltzmann-Shannon entropy functional, so which takes a probability measure rho m and gives the integral of rho times log rho with respect to the reference measure m. This was introduced by Boltzmann in statistical mechanics, and then it was studied also in information theory by Shannon. And for when n instead is less than infinity, we consider the Rényi entropy, which is the integral of minus n times the density rho to the power 1 minus 1 over n. And this also was introduced by Rényi in information theory, and it has also some counterpart in statistical mechanics as well. Okay, so here the message is the following. So I have the metric space X. I consider the space of probability measures by P of X, and then I consider some functionals defined on the space of probability measures. These functionals are parameterized by a parameter n, which later will play the role of upper bound on the dimension. So this n, you should think of it later as a kind of dimensional parameter. Okay, and I don't want to spend too much time on this entropy, but just two properties that is useful to keep in mind is that this Rényi entropy is always negative, apparently, and the key property is that the more concentrated is your measure, the closer to zero is the entropy. Okay, so the entropy is always negative, and the more negative the entropy, the more spread is your measure. The Boltzmann-Shannon entropy is kind of similar in the sense that the entropy is larger when the measure is more concentrated, but now the entropy goes to plus infinity if your measure is very concentrated close to a delta. Okay, but both entropies are lower if the measure is more spread. Okay. Okay. Now the beautiful connection with the Rigid curvature. Okay, so the beautiful connection was understood after the work of many people. Here I mentioned some key contributions, and the key fact is that if your metric measure space XDM is a smooth Riemannian manifold, then your manifold has non-negative Rigid curvature if and only if the Boltzmann entropy functional is convex along geodesics in the Bastien space. Okay, so in order to check the lower bound on the Ricci, it is enough to understand the optimal transport and the geodesics in the Bastien space and the convexity of the entropy along Wasserstein geodesics. So what do I mean more precisely with convexity along geodesics? I mean that for any two probability measures, mu0, mu1, so here I have mu0, here I have mu1, here I have the entropy. So I can find a curve, a geodesic mu t, such that if I draw the graph of the entropy as a function of from 0, 1 to r, it is convex. Okay, so it is a very simple condition. Okay. And what is the heuristic behind this condition? Well, the heuristic is basically the following. So here I have r, here is p of x, and now I draw something on x. So let me draw here the support of mu0, and here let me draw the support of mu1. Okay. So what is known by classical optimal transport theory is that the geodesic mu_t from mu0 to mu1 lives on t intermediate points of geodesics from support of mu0 to the support of mu1. So I have to consider all the possible geodesics which connects support of mu0, support of mu1, and then I know that optimal transport theory tells me that the support of mu_t is on these intermediate points of geodesics. Okay. Now, what is the intuition behind positive Ricci curvature? So, as I was mentioning in the beginning, think of the sphere. Okay. So, in the sphere, if you start, so what happens is that the geodesics tend to focus. Okay. So, if they start that they spread, then they will focus after. So, it means that in the middle, they are more spread than at the end point. Now, if the geodesic in the middle is more spread than at the end points, what is telling me about the entropy? It is telling me that the entropy at the end points is going to be larger than in the middle. And this is not a proof, but it is very much suggesting that the convexity could be a good thing to look at. Okay, so that's not a proof, but it is some heuristics behind this result. Okay. Now, why this result is particularly useful? Well, if you remember if you remember the topogon of triangle comparison, that was very powerful because it was giving a characterization of sectional curvature just in terms of a metric. Here, the key point is that we are characterizing lower bounds on the Ricci curvature just in terms of convexity of the entropy along Wasserstein geodesics, and that makes perfect sense in the general setting of metric measure spaces. Okay. Okay, and so this was the starting point of the theory because Lochsturm-Villani then defined a non-smooth space to have non-negative Ricci curvature if the entropy is convex along geodesics in the Wasserstein space. And these are the so-called CD0n spaces. Then one can define a more general notion of convexity and to take into account any lower bound on the Ricci curvature, and then one can define the CDKN spaces. So these CDKN spaces are kind of non-smooth spaces with a lower bound on the Ricci curvature by k and upper bound on the dimension by n. And this n enters into play because you consider the convexity property of the n-dimensional Rényi entropy. Okay? All right. So this gives the theory of CDKN spaces. So as we've seen, a smooth manifold satisfies the CDKN condition if and only if the Ricci is bigger than k and dimension is less or equal than n. The key point is that such a notion is stable under this weak convergence of Riemann manifolds. So now all the Ricci limit spaces of Gromov-Chigar-Kolding are example of CDKN spaces. And many of the classical geometric properties, for instance, Bishop-Gromov volume comparison, hold in this non-smooth setting. Okay? And if you're interested in kind of more general structure than Riemann structures, the so-called Finsler structures, so meaning that on any tangent space you put a norm instead of a scalar product, then this CDKN condition is flexible enough to allow for Finsler structures. Okay. But if instead you are more interested in Riemannian geometry, so really having a scalar product which is not a norm, then maybe you would like to refine this non-smooth, this class of non-smooth spaces to isolate the Riemannian non-smooth structures. And the idea is to look at the Dirichlet energy, which in the non-smooth setting is called Chigar energy because it was studied by Chigar. And the key observation here is that if you have a Finsler manifold, then the Chigar energy, so this Dirichlet energy, is a quadratic form in the sense that parallelogram identity holds, if and only if your manifold is actually Riemannian. So a good way to discriminate between a kind of non-smooth Finslerian structure with respect to a non-smooth Riemannian structure is to look at this function and check if it is a quadratic form. And so the idea by Ambrosio Gigli and Savaret was to reinforce the CD condition by asking that the Chigar energy is quadratic. And so they define this notion of RCD, Kn spaces, which are Riemannian, which is the so-called Riemannian curvature dimension condition. And by definition, a multi-measure space is an RCD-Kn space if it is a CDKn space and the Chigar energy is a quadratic form. Okay, so this is the definition. And now there are many good properties that this space is satisfy. Stable under pointed Mesogonoff convergence. So again, all the Ricci limits are included in this class. If one is interested to the heat flow, one can characterize the RCDK infinity condition just by looking at the contractivity of the heat flow. It is equivalent to the Bochterian quality, so which is a very powerful tool in Riemann geometry. Once one has the Bochterian quality, one can prove the Liao inequalities on the heat flow. One can prove also the Chigar-Romo splitting theorem. And once one has the splitting theorem, one can start to study the infinitesimal structure of these spaces, basically by iterating the splitting theorem. And what one can prove is that these spaces are non-smooth, so they can have singularities. But at almost every point, if you dilate your space more and more and more, your blow-up will be Euclidean space. Okay, and more precise and more strongly, your spaces are also rectifiable in the classical sense of geometric measure theory, in the sense that you can throw away a subset of measure zero and cover all of the rest with the Lipschitz charts into a Euclidean space. And more strongly, these charts take values in a Euclidean space of fixed dimension, which is work of Bruenz. Then one can also study the topology of these spaces by studying the universal cover. So that they admit a universal cover, and the universal cover is still an RCD space. One has the Loga-Dulova property, and one also has good properties on the isoperimetric profile. And one can prove sharp isoperimetric inequalities and Sobolev inequalities. Okay, now a lot of good properties. Now, how rich is the class of RCD spaces? Are we just having many good properties because we are speaking of the empty set? But no, there are many examples. So as we've seen, all the limits of Riemannian manifolds are RCD. Then Alexander spaces, so those spaces that I was mentioning in the beginning with lower bounds on the sectional curvature in a synthetic sense using triangle comparison, are also examples of RCD spaces. One can produce RCD spaces also by multiplying the volume measure of a Riemannian manifold by a weight and checking that the so-called Barchi-Emery Ricci tensor is bounded below. One can take cones or spherical suspensions over RCD spaces, or taking quotients of manifolds or orbifold with lower bounds on the Ricci and still getting an RCD space, or considering stratified spaces with lower bounds on the Ricci. So you can see that, say, the class of example is quite rich. And now I want to, so now what we've seen is that the definition, some basic properties, a class of examples, and now I want to give a quick overview of some of the applications that this theory has found in the recent literature. And more generally, the applications of this way of looking at Ricci curvature with optimal transport. Okay. So a first application is to Ricci flow. Indeed, an important result in Ricci flow is the Perelman-Theodor theorem. And it turns out that in order to apply the Perelman-Theodor theorem, it is important to have a almost Euclidean isoperimetric inequality in balls. And this was proved by Cavalletti and myself. This almost Euclidean isoperimetric inequality in a ball with almost no negative Ricci and almost maximal volume was proved by Cavalletti and myself using optimal transport tools. And this permits to apply in a more easier way this theorem by Perelman, and indeed enabled Liu and Zehelidi to extend some previous work of Donaldson and Thun, proved previously for manifold with double bound on the Ricci to just lower bounds on the Ricci. Then very recently, there's been a proof by the Hamilton conjecture, which says that if you have a three-dimensional manifold with Ricci bounded below by constant times scalar, then the manifold must be either compact or R3 or flat. This was proved by Deruel, Schultz, and Simon, and Lee and Topping after previous work of Lott. And there, a key point in the argument is to prove it by contradiction. When you argue by contradiction, you have to take limits of smooth manifolds. In the end, you arrive to a non-smooth space, and an important step in the proof is to work on this non-smooth space, and the RC theory plays an important role there. Then very recently, just a week ago, jointly with Brouet and Semola, we posted a paper where we answered to an open question by Perelman and Petrunin on the existence of an infinite geodesic on every Alexander space without boundary. And our work builds on top on recent work by Kapovic, Lichank, and Petrunin, where basically they show that if something called measure boundary is equal to 0, then the solution, then the conjecture of Perelman and Petrunin holds. And what we do is we prove this condition, this fact that the measure boundary is equal to 0, but in the much more general framework of RC spaces. And so this is how, say, the theory of RC spaces can be also useful to answer questions in other fields, because it is very general. Then there are connections with string theory. Indeed, in recent work with the two friends from physics, De Luca and Tomasiello, and with De Ponti, what we realized is that in string theory, what is well known in string theory, that usually you work with spaces of, say, 10 dimension or 11 dimension, and there are some singularities which are very important in string theory. And what we realize is that these singularities are of RCD type. So these kind of non-smooth spaces which arise in string theory are example of RCD spaces. And then one can apply or say modify the theory of RCD spaces to answer some questions there. And for instance, say the Laplacian operator in the RCD setting corresponds to the so-called Kaluza-Klein operator. So the spectrum of the Laplace operator corresponds to what is called in string theory as Kaluza-Klein spectrum, and then one can use this correspondence to answer questions in string theory. Then there's connection also to general relativity. Indeed, this optimal transport formulation of lower bounds on the Ricci curvature works well also when your ambient space is a Lorentzian manifold. And when your space is a Lorentzian manifold, then Ricci curvature is intimately connected with the Einstein equations. Indeed, one can formulate the Einstein equation just in terms of the Ricci tensor and of a manipulation of the energy momentum tensor. And so one can use optimal transport to completely characterize the Einstein equations, and one can use optimal transport to extend some classical results of general relativity to a lower regularity setting. For instance, we have done it for the Hawking singularity theorem. Okay. Then there are some beautiful connections and beautiful application to isoperimetry. For instance, recently Antonelli, Brouet, Focagnolo, and Pozzetta proved the existence of isoperimetric sets in non-compact manifold with lower bounds on the Ricci and a control on the volume growth at infinity. And Antonelli, Pasqualetto, Pozzetta, and Semola proved some sharp concavity inequalities on the isoperimetric profile in non-compact manifold with lower bounds on the Ricci. So this kind of inequalities were already known for compact manifolds by classical work of Bavard, Pansou, and Bailey, but it was an open question if they were true also when the manifold is non-compact. And there the problem is that you can have is to study what happens at infinity and take the limits at infinity. And there the theory of RC spaces is really key. Okay, so this is a quick overview of recent applications. So it's time to conclude. So the final message of this talk that I would like to convey is that in doing Riemann geometry, one naturally encounters non-smooth spaces. Okay, so when one takes limits of smooth Riemann manifolds, and taking limits of smooth manifolds is done very often in modern geometry, for instance, in contradiction argument, blow-up arguments, studying singularities in geometric flows, or one encounters singularities when taking quotients or cones of Riemann manifolds. So what we learned is that if the smooth spaces we started with have lower bound on the Ricci, then the non-smooth spaces which arise are RCD. So this class of RC spaces form a natural class of weak Riemann manifold with lower bounds on the Ricci. And the big advantage of this class of RCD is that it is closed under natural geometric construction, like taking limits or taking constants or taking foliations, which instead force you to go out of the class that we all know and love of smooth manifolds. Okay, so if just let me end by a small advertisement. So if you are interested in this kind of topics, follow the talk of tomorrow by Daniele. We have to wake up early because it's at 8:30. And I wish to thank you for your attention and happy birthday to Emanuele Italiano and everybody.
The Riemann manifold spaces.
Yeah.
Is it possible when I know just the metric and the measure to realize that come from Riemann? Can you see the Riemann structure from? I mean, the measure is not in the measure. Right? Can you see it from the measure space?
In the case of a Riemann manifold, the measure comes directly from the distance because it's the Hausdorff measure, right? So you can check just for that, but the distance is much more complicated. It's not something that you can just see the distance as well. Yeah. So for the Finsler, you can see it. Usually, you can check it with a blow up. So if you delete in the Euclidean setting, you are going to see Rn with the scalar product. In Finsler, you are going to see Rn with a Finsler product with a norm. So you can check it by a blow-up argument.
So if you start from a compact surface, in that case, having a Riemannian metric is essentially the same thing as having a complex structure. Mm-hmm. So in that case, there are very well studied spaces of limits because these are the moduli spaces of Riemann surface.
Yeah. Yeah.
So my question is whether it is you can interpret it via these limits of this RCD space, the limit spaces you are talking about within the framework of moduli spaces of. What would that be? Because these are, I mean, you really have a singular space in that case with particular singularity. Right. And whether also in higher dimension.
This is a very good question. So it has not been done yet. My feeling is that it goes a little bit in a different direction. So you said that the complex world is very rigid and more regular than the smooth world, while here we're in a direction which is, I think, I would see as the complex manifold that's very rigid, then smooth manifold that's less rigid, and then the spaces are much less rigid than manifold. So this is how I would see the things. But say one can think of describing also a complex structure probably in a synthetic setting, at least for a subclass of RC spaces, which are the one with an n-dimensional measure. In the sense that once you have that all the tangent spaces are n, then you can talk of a complex structure over the tangent spaces, and one needs to understand say how say the change of coordinates basically to have a globally defined complex structure. In this setting of RC spaces, the challenge is that you are not covering your space with open subsets with values in Rn, and you cover all the space, but you have always to throw away a singular set, usually of dimension 2 in the and that's not so clear to me if that's enough for defining a complex structure globally. But it's a good question.
Is there any kind of embedding theorem to this kind of structures? So can you realize RCD spaces into affine spaces?
Right. So there's a not really in Rn, but there's a work of a couple of years ago by Ambrosio, Honda, Tevodros, Porteges, who realize an RC space by embedding it into an infinite-dimensional Hilbert space. So basically, you use the kernel to embed your RCD in an empty space.
And there are counter examples for the finite dimensional space.
I don't know.
From an RCD space with isolated singularities, for instance. So if you have this assumption, the singularities can be infinitely many, for instance.
Yeah, they can be dense also. Yeah, they can be many and dense, and this is quite easy to see. For instance, you can take so here you have a cone. Instead, take a tetrahedron. Okay, let's see the tetrahedron. Okay, this is 4 singular points, right? Now, on each face of the tetrahedron, you can construct a smaller tetrahedron. Okay, and you have then the double of singular points. Then you can iterate this procedure and you double the number of singular points. Since this notion is stable under convergence, you will see that the limit is still an RC space, but then it will have infinitely many and dense singular points.
And so they are singular spaces that are very different with respect to algebraic spaces, algebraic sets that have a controlled topology and also singularities. So,
right.
So in the compact case, they are very.
Yeah, and also the topology can be very wide, so there's no control on the topology.
Can you advise NC STD there's a limit for smooth stuff or
No,
the singular isolated points?
Right. So if the question is, can you realize? So what you know is that every if you take a limit of n-dimensional manifold with lower bound reached by k, then the limit is an RCD space. So the question I think is it true that any RCD Kn space is a limit of manifold of a small dimension n and lower bound on the reached by k? And yes, is no. So there's a counterexample, and the counterexample is a cone over RP2. So take RP2, take a cone over it. Then this is a three-dimensional RCD 0 space, and it cannot be achieved by a limit, by a deep result in Ricci flow, which tells you that all the three-dimensional limits of manifold with lower with non-negative Ricci are topological manifolds. This is a result by Simon and Simon Topping, whose proof uses the Ricci flow. And why this is interesting, because then this cone over RP2 cannot be is not a topological manifold, because we have a topological singularity at the tip of the cone. So it cannot be achieved as limit of manifold, because you know that all the limits must be topological manifold. You have a space which is not a topological manifold, but it cannot be. So it cannot be approached by itself. So we can thank
Now we have the configuration ground floor as before. Then we restart 3:30 on time the parallel session, because then at 4:30 we'll be back here for the roundtable on applying mathematics to biological further science.
No, ma così funziona bene.
Oh,
Sì, ma certo non è che... 1, 2, 3, prova, prova. Perché io volevo stare un po' al lato per stare al centro, però... perché così sta un po' più al lato, loro tre stanno al centro. 1, 2, 1.
Questa è una box di microfoni. E quindi vuol dire che c'ho... Ah, è qua! Guardalo che è lì.
Questo? Ok, è uno. E loro parlano tutti lì?
No, state seduti. Prova. Prova. No, non è acceso.
Posso scorrere le slide un secondo?
Sì, tanto non sono proiettate. Chi cura la proiezione?
Dovrebbero esserci tecnici.
Ah no, aspetta, queste di là
Eccole qua.
no,
Vedi che adesso...
sono proiettate.
Allora questo qua lo teniamo in mano?
Sì,
Ah, ma secondo me ce l'abbiamo due.
Una che posso uscire un attimo.
No, no, allora lascia.
Uno tengo io. Eccoci, uno lo tengo io, no, di microfono. Fabio lo tengo io. Sì, sì, no, io metto il di lato, ragazzi. Ubi Maior.
Copriamo lo schermo.
No. Allora, anche se... Just 2 minutes to start the session. So, quindi forse un altro microfono c'è. Questo...
No, solo questo.
Sì, e come facciamo? Quindi ce lo passiamo? Ok, va bene. Allora ci avremo il microfono da passarci, ragazzi. Va bene, va bene.
Se volete parlare,
Magari qualche... Tanto qui si sente, e sono quelli in... Ma se sto qui si sente anche lì?
Sì, si sente anche lì.
Ok.
Quella è la qualità migliore.
Ma lo spengo o lo tengo sempre?
E li spegno quando si sente. Vabbè, no. Ormai dopo fate la presentazione e salutiamo.
Adesso cominciamo subito.
Ok.
E quindi rimane qui, ci faccio adesso. Grazie. Non ci lasci soli. Ok.
Se volessi utilizzare anche il pointer, basta che lo switcho.
Sì, durante
ok. Speriamo.
Qua stiamo proiettando. Sì, sto staccando. Grazie.
Io parto dai piedi qua, quindi parlo così.
Sì, sì, sì.
Va bene.
A volte magari si parla in quel
Va bene, va bene, va bene.
Ma si può spostare questo?
No, è incollato. L'ho già provato.
Perché non vieni qua davanti? Di qua?
Va bene, so good afternoon. Welcome to this round table with this quite fun title, 11 square years after Volterra, primary knowledge to biological and social sciences. This session is devoted essentially to biomathematics, social sciences, and so on. Mathematics applied to new fields, at least when Volterra started this kind of studies. And our source of inspiration was this public speech made by Volterra in 1901 in Sapienza in Rome, when he gave a talk for the beginning of the academic year. And in Santivo Sapienza, which is the old central headquarters of Sapienza in Rome, near Piazza Navona, and get a vision, a sort of a sketch of future mathematics, application of mathematics to biology, social sciences, economy, and so on. It was completely visionary because at that time nothing existed really in these fields, and
Mondino was one of the first, but 25 years later, to start this kind of studies. So if you read, it's possible, it's available online in Italian, the original transcription of this speech, you can feel the flower of this great vision of our grandfather, scientific grandfather, in some sense. But there was also the founder of CNR. I am Roberto Adelina, I am the director of the One Institute of Mathematics, Applied Mathematics in CNR in Rome. And so, in some sense, and also people, all mathematicians applying mathematics to biology, to social interaction between individuals are in this, they are following the track marked by Voltaire 121 years ago. And so today we have also the honor to have one of the nephew of the grandchildren of Vito Voltaire. The family. Sometimes we have the family, and we have a good relationship also with his cousin Virginia in Rome, and so also maybe you can the salutation to Virginia. Maybe she's online. I don't know, and so maybe we can start this this rendezvous, which is on these subjects of biological and mathematics and social sciences. And even other, maybe other kind of application of mathematics which were not even mentioned by Voltaire at the time. We have three speakers, three exceptional speakers, and which are experts in their fields at international level. And first of all, we have Ilaria Rigatti, and maybe I can give just a short sketch, but in the following, maybe we can discuss also your career. But anyway, Ilaria received the PhD at the University of Trento some years ago. We don't specify the age of anyway, but she's very young, so that's not a problem for her. And then you become a lecturer in London Imperial College, and she works on models in epidemiology. And maybe you have found some interviews with Ilaria, even Italian television and the radio and so on. So she's quite popular. She was quite popular before the pandemic, but I mean, it was the opportunity for her to become quite well celebrated in Italy for her capacity also to attack real problems. And this study on Vo, near Padua, finally, is what the first study in the world about this pandemic, and maybe the most cited, I think, on this topic. Then we have Massimo Forlasier. I'm just going not to the age, but the lexicographic order. Okay, and so Dorigatti, Forlasier, Piccoli, and also the age in some sense is important. And just to say that Benedetto is very old.
Yeah, exactly.
And
The age of Voltaire.
The age of Voltaire, more or less.
More or less.
I don't know which Voltaire.
But I am the grandfather of Voltaire. So anyway, Massimo Forlasier is quite a pure product of Padua University. He graduated in Padua, and then he got his PhD here. And then he worked in Rome, in Vienna, and now he's professor in Munich. And she's a chair of applied numerical analysis at the Technological University of Munich. And his interests are really huge, in my opinion, starting from image analysis to the study of behavior of crowds or collection of individuals and many other things. So that's I don't want to spoil what you do, but it's really quite impressive your CV. And finally, Benedetto Piccoli, who is also a former Padua student. And so there is something common that the three of them, they are from this region, more or less. Trento is near near Padua anyway. And then after the degree here in Padua, he left Padua to go in Trieste, where he got a PhD, and then became a professor. First researcher at Trieste in Sissa, and then professor in Salerno. Then director of research in my institute in Rome. I'm quite proud that he spent 8-9 years or something like that in my institute. And then he left Italy to go in the United States to reach his glory and in the Rutgers University in Camden. And now he's, I read because I don't know what it means, but the vice chancellor of research in Rutgers University, that's something like vice president, who knows, vice rettore, something like that. And then also he was the director of the PhD school, something like that, in Camden. And his research were many fields, starting from control theory, then fluid dynamics, traffic theory, and now biology maybe is the main line of research, even if traffic is still in Europe. Okay, I was even too long. Now that's the time to start with some first round of speeches, sort of a small introduction to this topic. So I ask the speakers to be not too long, just to give some impression, not too technical also. But I know you are well prepared. So, Ilaria, it's your first round.
Okay. So thank you very much for the kind introduction, Roberto, and thank you to the organizers for really inviting me and all of us to this quite amazing conference. Thank you for your hospitality. It's been great to be here. Thank you to Unione Matematica Italiana for giving me the opportunity to talk to you about what I do, which is applying maths to medical sciences. And I'd also like to thank all my colleagues and the people I work with at Imperial College COVID-19 response team, all the colleagues at the University of Padova, Azienda Ospedaliera di Padova, University of Trento, and many other institutions. And of course, thank you to the funders, without whom we can't really do the research that we do. So I'll give you a little caveat and just a disclaimer. This is a bit of a different talk as compared to the talks that you have seen before. There is not a single mathematical equation, not a single mathematical symbol, right? It's just pictures, and you will see some quotes. And these quotes come from the speech that Vito Volterra did in 1901 for the inaugural, to just open the academic year, in his famous speech. And I did it because it was quite striking to me to see how, despite the theory and the mathematical models for applied to biology were not really fully developed at that time, he had this vision, and he could clearly see how we are currently using, maths applied to medical sciences 121 years later. So, of course, I couldn't keep myself from starting by talking about COVID-19. So this is, the biggest pandemic that we have all experienced. It's the biggest pandemic in the last century, and it has affected our lives. We know it very well in the last couple of years. Thank God we are now coming out, hopefully, from this pandemic. We have the opportunity to be here together. And the scientific consensus is around the fact that this pandemic has really natural origins. So that means that there has been an event of spillover from the animal reservoir into the human population. And we know that these sort of events are rare. So there is a very small probability of an epidemic, a spillover event happening. But because we are mathematicians, we also know very well that because the probability is small, it doesn't mean that events do not occur. they occur, and actually we've seen that this happens. And mathematical models are a very powerful tool to explore and to reconstruct what are hidden processes. And one of the hidden processes in my field is the infection process, because we cannot observe it, right? We see the number of new infections when they show symptoms, we see the number of hospitalizations or deaths, but we never see the events, like the infection process events happening, because this is just, surveillance is not done for really observing this sort of events. And so maths is a very useful tool for reconstructing hidden kind of processes. And one of the things that we did very early on, it was January 2020, was trying to reconstruct what the size of the outbreak in Wuhan was. And we did it by looking at the number of people that were exported from Wuhan. And that gave us quite a good indication of actually at the time, and this was kind of the first report that the Imperial College COVID-19 response team published very early on in January, and it raised the alarm bell around, there being an outbreak ongoing of this new coronavirus. We didn't know it was SARS-CoV-2 at the time, essentially because, the 41 cases that were reported in Wuhan were not really comparable with the size of the epidemic that should have been in order to explain the 3 number of exported cases elsewhere. And so we kind of demonstrated that the size of the epidemic in Wuhan had to be considerably larger. And so there was really an outbreak ongoing and likely human-to-human transmission. And mathematical models can be applied to really characterize what is the epidemiology of a new virus. And so every time a new virus emerges, we really do not know what the characteristics of this virus are, and we need to characterize them. So maths really help us doing this. And I'm talking about, for instance, times and delays between the onset and hospitalization and onset of deaths, because all these quantities really help you to reconstruct and kind of push backwards and try to infer how many infections you have in the population according to the data that you observe, which is just a small proportion. And I had the privilege really to work with the University of Padova at the very beginning, at the very early stages of the pandemic. And specifically, I worked, as Roberto introduced, on the case study of VO, which was really at the forefront of the response in the COVID pandemic. Why? Well, because in VO, we did 2 mass testing surveys, like we're talking about swab surveys, so looking for the virus, at a time where testing wasn't even recommended. In VO, a 2 weeks lockdown was imposed very, very, very early on, at a time when outside of China, no one had imposed any restriction against COVID-19. And then in VO, we followed this population through 3 rounds of serological surveys. So we looked for antibodies in the people who were infected to understand better whether the immunity lasted and how the immunity was changing in time. And these studies really gave us a wealth of information. Really, we understood so much from this cohort in VO. We understood, first of all, that there was asymptomatic infection. It's something that we really didn't know at the beginning, at the time of the study. And actually, we found that a fair proportion, 40% of the people tested had not symptoms at the time of test and didn't have symptoms even afterwards. We learned about the efficacy of these interventions because lockdown and mass testing were incredibly effective at really shutting down the epidemic. And at the same time, we learned that contact tracing, as it was done at the time, was not particularly working. So it was manual contact tracing, which was not particularly effective. We learned about how SARS-CoV-2 spreads not homogeneously in the population. So the number of secondary cases that an infection produces is not equal in the population. Most people produce no new infections, but a few people produce a large number of infections. These are the super spreader events. And we quantified from VO that 20% of the infections are responsible of 80% of transmission, which is an estimate that has been validated all over the world. And also we understood that immunity, regardless of whether it was given by natural infections or vaccination, is decaying in time. And this is just a characteristic of the immunity given by this virus. working? Did something happen?
Not really, not really.
Oh, got it. Sorry.
Yeah, okay, thank you. And the processes, like the infection process and the processes that we observe are complex. So we are aware that they are very complex. We need to learn that they are from their complexity. We need to acknowledge the complexity. But as mathematicians, we just do not want to model its entire complexity because we would fail. And so we need to be very aware of the limits of our models. And so what we do as mathematicians, we need to understand what are the main characteristics of an infection, try to identify what are the main features, like is age important in this infection? Yes, for COVID-19, so we need to include age, we need to do these sort of reasonings, and really try to identify what are the main drivers of an infection. But in the end, we need to simplify, we need to make a work of abstraction and simplify the natural complexity of the phenomenon in order to write it down into mathematical formulation that then we can solve. And one of the first models that everyone learns when they do mathematical applied to epidemics is learning about the SIR model. And this is an example of a simple model, because essentially what we do is we classify the people into compartments. We just say that people differ by their infectious status. They are either susceptible, or they are infected and infectious, or they are recovered and immune. We completely ignore the fact that there are individual level differences, like age, any sort of difference that just make us unique and different people, one from each other. And even though then, of course, we do not stop at the simple SIR model, we can add age structure, we can add spatial structure, we can have different risk groups. But even if we keep adding some classes, they're still limited in number, and they just do not capture the true complexity that is reality. And still, this is a good thing though, because with these models, relatively simple, we do a good enough job at really understanding what are the processes that really govern and drive transmission, and we can reproduce the data typically fairly well. Models are useful for making projections, for looking forward. So once that we have a model that can reproduce the observed data, that means that we have, first of all, understood a mechanism, the mechanism of infection. Then we have understood the parameters of the model that give us, the observed data. And then, of course, in reality, we cannot go to tomorrow. We just need to wait for tomorrow. But with a model, we can just look forward. It's just a matter of letting the model run in time forward. And this is the beauty of having a model, because we can see what we can expect from tomorrow, from a week, from a month, in the future. And at the same time, I think we need to be very clear that models are not a crystal ball. They don't know, they don't tell us, what's going to happen for sure, because models are a useful tool to explore scenarios. And what do I mean by scenarios? Models are a tool to explore, for instance, how many numbers of new infections I will have if, for instance, the transmissibility of a new variant is higher or lower than the current one, or if population mixing will stay the same or will increase in the future. But the model doesn't tell us whether, the new variant will have higher or lower transmissibility, whether people will change the behavior in one way or another. These are simply things that, we need data, we need to understand from the data, we need to characterize these characteristics from the data, and then we can, use them essentially into the model. And at the same time, despite there are these limitations, and despite we can explore scenarios, for policymakers, it is incredibly useful to know, what's the scenarios that they have ahead of them. So what's the best and the worst case scenario? Why? Because effectively epidemics can be changing the trajectory, and we've seen that. So in case a scenario is too bad, in case the outcomes are not really acceptable, regardless of what acceptable means, different governments have different opinions of what is acceptable, well then new interventions can be put in place so that the worst outcomes do not occur. And in this sense, I think that there has been a bit of, some misunderstanding sometimes in terms of media and newspapers around, what are these scenarios? And we have seen, for instance, journals and newspapers maybe just mentioning that models got it wrong, or that, the predictions were completely out of reality, when actually I think, it's just a misunderstanding of what models can and can do and what the meaning of exploring scenarios is, because you can't just compare the number of observed cases in a population with the number of projected cases obtained under different assumptions. It's clearly the two things are not matching, and so it's not a fair comparison to do a comparison between these two things. So I think, just looking forward, I think we should probably do a better job at communicating what scenarios are and at communicating what models can and can't do and what is uncertainty around our predictions. Going forward, and I don't want to stop on COVID-19, but models are a very useful tool to explore hypotheses. And you see two little pigs here, because this was the first project first paper that I did when I went to Imperial, which was really analyzing H1N1 data on the 2009 swine flu pandemic, where effectively England had a third wave of infection, which was completely unexpected. And so the question was, why do we see this third wave when actually no one was expecting a third wave? And so we did kind of a hypothesis testing exercise, which really highlighted how the third wave was due to an increase in transmissibility of the virus, which then was indeed demonstrated and confirmed by lab work. So essentially the virus had mutated not in the antigenic site, but in other parts, and it became more human-like, more able to infect the human cells during this time. And it did it completely undetected. And this testing of hypotheses doesn't just stop on really wanting to reproduce the dynamics of an infection, but also is useful when we want to characterize what is the impact of interventions. And so, for instance, we do hypothesis testing when we want to characterize the mode of action of vaccines, for instance, and in this sense, we work at the population level, so our unity is the individual. But we do very much the same work when, for instance, we look at mode of action of drugs. And in this case, we work at the cellular level. So, but from a mathematical perspective, there isn't really much difference in terms of the tools that we use. And so in this case, for instance, really we look at, how the drug, these are drugs that are currently in development, are, affecting the pathways, how they are really, we are trying to understand how they are working at the cellular level, and whether, the mode of action that we see in vitro is the same for mice, for non-human primates, and so on. Models are a very useful tool to understand and to reconstruct the past. And here I am referring to what we call sort of catalytic models, where essentially we use serological data. Serological data are data on antibodies that we find in the body of the people. And usually we do cross-sectional serological surveys. So at a certain point in time, we screen people from different ages. And this really allows us to estimate what exposure this population had, what kind of transmission there has been in the past. And this is important because the type of interventions that you apply in the future really depends on the type of exposure that the population had in the past. So the effectiveness of interventions is not the same everywhere. It depends on the transmission setting of specific locations and on the history of infection of the populations. And so this is why it is important to really understand the past, to project into the future, and to apply the resources that we have in the best possible way. What I do most of the time is do model calibration. And so there are established and rigorous and, inferential frameworks that work well. And, when I started, I had to code these models by myself, and now things are becoming increasingly easier in the sense that there are packages that allow you, to quickly fit models. I must say there have been great, improvements, but in a way we are still constrained computationally, because sometimes we are ambitious and we would want to fit fairly complex models, and we are just a bit constrained by the computational time. So I think that going forward, it is important to keep talking among us mathematicians, both the applied people like me and the people who develop maybe methods like you, because really, if we want to push forward, you know, the kind of the frontiers of medicine, of maths applied to medicine, I think it's useful to understand that we need to work together. We need people who develop methods. We need numerical analysts. We need computational, you know, improvement into the computational side. We need software engineering that can really implement these tools in effective and efficient ways. And so I hope that this gave you a little overview of what I do and maybe gave you a little inspiration as well.
Okay.
Sì, c'ho.
Grazie.
So, first of all, I'm very happy to be here as well. So, it has been an exciting week with a lot of amazing mathematics and very inspiring talks. And for me, it's always a pleasure to be back in Padua. So thanks a lot for inviting me here. So the topic that I want to mention and to tell, it's about mathematics that one can use for explaining social dynamics and how, say, what the lesson that we learned from the mathematics that describe social dynamics can actually inspire mathematics itself. So it's a kind of duality between the two fields that may seem a little bit bizarre, but then I will try to convince you that some of the two things can go two ways. So from what Ilaria was mentioning, there are some models that people are using. She mentioned this SIR model, and this is a differential model. So differential equations are one tool that was actually invented to describe physics, but somehow in the course of the years, mathematics was allowing to go beyond somehow physics and try to explain phenomena that are significantly more complex. First of all, because in physics, the physical laws are always the same. They can be reproduced, they can be tested, they are always confirming their effectiveness. And to a certain extent in biology or say social sciences, most likely the first principles are hard to understand, to test, and most likely they change in time. And so it's kind of unbelievable that one can use a mathematical method to really describe something that has such a variability in its own field. But still, it seems that, of course, calibrating method and models to certain circumstances, which means that they need to be adapted to the particular phenomenon and maybe adapted to the particular phenomenon in a certain time, still it's allowing us to describe the fundamental essence of the phenomenon, maybe doing also some predictions about that, and even obtaining some fundamental insights. For instance, maybe you have been seeing some of these phenomena like birds flying together, having a very beautiful smooth behavior in the sky, or even a school of fish forming meals that are rounding in a coordinated manner, and it's almost a mystery how come that they do that, right? But then by analyzing a little bit the behavior and trying to look at the first principle, it turns out that by requiring that every fish is basically attracted by the others, but it does not somehow want to collide with these others. At the same time, the fish would move with a preferred velocity. These three fundamental mechanisms are sufficient to be able to reproduce exactly the formation of such meals. And this is amazing that a individual decision of a group can eventually form such patterns that are very interesting. However, we experience such patterns also in human dynamics, right? So if you think, basically, our society is often divided into opinion groups or parties, and somehow we do structure the decisions actually in our society according to this grouping and some homogeneity of views about the society, right? And also these things can be, to a certain extent, modeled, and we can try to understand how come, in a certain sense, a population in time can blend its own opinion to form individual parties, for instance, right? These kind of models are very simple. Here we can see one of them. It's actually a little system of ordinary differential equations. But somehow this system of ordinary differential equations, despite the simplicity and most likely the fact that it won't reproduce data in every circumstance or in every moment, one would have to calibrate this model all the time, might allow us nevertheless fundamental insights. One of these insights is maybe the fact that we can understand how societies can be controlled. So this is coming from the blog of Terry Tao, a Fields medalist in 2010, and in this blog about the theory of infield games, he has been writing that it would be interesting to understand what happens whenever you have a group of, in a population, you have a part of this population that acts as leaders within this population. It would be very interesting to understand how can we describe the influence of these leaders over a population. And it turns out that if you try to apply this idea to the opinion dynamics, you can obtain certain theorems that could explain some of the effects that are known in our common experience, which is this theorem that actually did with Benedetto. And these theorems tell you that in a population that is trying to blend the opinions and in principle form parties, if now we allow an external agent to influence the opinions, it's possible with parsimonious interventions. Parsimonious intervention means that you try to influence the minimal number of agents for the minimal amount of time, okay? With such parsimonious interventions, nevertheless, it's possible to induce in the group any opinion that one wants. This means that without media, without having a variety of opinion leaders, it's possible to induce very, very quickly an entire population to believe into some opinion. So this is something that we are experiencing right now in certain countries that we know, and it's of course a very tragic somehow fact of human dynamics. Of course, with this kind of tools, you can do also good things, not only somehow control society for the bad, but maybe using a certain kind of controls to help certain people to find the exit in a building. Maybe these people are trying to escape, they need to be evacuated. Those people that can't see the exit can get out, but those that do not see the exit may have to walk around and explore the environment. In the second dynamics that you can see, it is possible to a certain extent to induce the full evacuation of the entire population, exclusively coordinating the group through the action of a very small amount of agents. And so this is a surprising effect that nevertheless is related to the previous phenomenon of the fact that we can induce opinion formation by parsimonious interventions. Okay, so that's about a little bit how we can see, say, the fact that populations can be controlled and described by certain population dynamics, but there is also the other way around. So now we know that multi-agent interactions are able to form certain patterns, so they can be coordinating in a good way. And there are some problems in mathematics that needs to find solutions, right? And so many problems in mathematics may have even just a mixed solution. And what the mathematics are trying to do is to either characterize these solutions or finding those solutions through maybe a numerical method. But then why don't we try to generate and create a population of agents that, inspired by biology, they are basically trained to find solution of mathematical problems. So now it's the biology or the somehow the social dynamics that do inspire for mathematics. And how do we do that? Well, one of the most interesting problems that are remaining in the numerical world is how to solve global optimization of non-convex functions. We have seen this kind of problems coming up in artificial intelligence quite a lot. In particular, in very high dimension, this is a very, very difficult problem. And here we can see an example of a function that have zillions, let's say, of local minimizers that would fool most of the algorithms that are out there. But we can, in a certain sense, design a certain multi-agent dynamic inspired by biology that is trying to learn actually where the global minimizer is and to converge there in a very fast way. More or less just following an opinion of the particles where the global optimizer is supposed to be, and then in a certain sense, finding a consensus and dropping there altogether. Okay. So these kind of things can go even in more sophisticated dynamics. You can think to solve problems even on objects that have variable curvature, and say going into situations that are really, really difficult. This is amazing how, in a certain sense, what could be inspired by biology that has been so successful since we are all alive and we are sentient beings, means that biology found good ways to solve problems. We can use this to solve our problems in mathematics. Okay, thank you very much.
Thank you. The next optimization problem is to use all the same software on the same computer.
That's impossible.
It's my fault. Yes. Sorry.
Oh, well.
Yeah.
So, Benedetto, it's your turn.
Thank you very much. So as my colleagues, I have absolutely to thank a lot of people, but mostly University of Padua, UMI, and the department for this fantastic event, Roberto, for coordinating this table. And we are talking about 11 square, 120 years of Voltaire, but we have another amazing square, the F square, the Fabio and Francesco, without whom, you know, this event wouldn't be what it is. So having said that, I wanted to talk on the line of Ilaria and Massimo about the different concepts and different languages. And so most of us are mathematicians here. And when we talk about models, we think like in the Volterra case, mathematical models. But when you interact with medical sciences, this is a paper of 2018 from US FDA people, Food and Drug Administration. So is the governmental agency that is responsible to approve medical treatments and devices. And you see that indeed the most commonly used models are this one, animal models, because, you know, we want to cure humans, also animals, but, you know, most possible humans. And we are using animals to mimic what would happen in humans. That's, I mean, it's very well known that for experimenting some drugs and medicines, we use animals. Then there is the bench. The bench means biologists using cell lines or other type of cells that experiment the same type of drugs or other medicines. Then there are clinical trials. Clinical trials are people that are recruited on which some treatment is tested and then controlled and so on. But you see that in 2018, probably for the first time, FDA indicated computer and mathematical models as a model. So what we call models is 121 years. Finally, the medical science is recognizing this is a model that can be used for medicine to explore cures and other things. This doesn't work. I will show you in the next slide another picture from the very same paper. Again, I'm talking about 2018, so it's only okay, here we go, only 40 years ago. And beside the fact that 121 years after Volterra, they are recognizing models, they are indeed doing a quite good job in saying, okay, they are not only useful, but they are useful for a lot of things. And you know, you can see here, you mentioning we can simulate device, anatomy, all the way to treatments, clinical trials themselves. That is extremely important. This is a very, you know, growing area. Simulated manufacturing of 3D devices like stents and so on and so forth. Obviously, using mathematical models instead of those other models have an enormous advantage, both economically, but also from other point of view. Imagine that you don't need to recruit people, at least, you know, not at the scale that is done now for testing medicine, but you can use computers. Well, it's much safer, right? We don't care if a computer model goes wrong. We care a lot if there is some problem with people. But what is the problem, the real problem in using these models? Well, you know, especially people that are used to deal with physical systems, I don't know, computational fluid dynamics, so difficult. I agree completely. But then take a look at this. This is one proposal of how it should work the human metabolism. It's from 2019. Well, it's updated to 2021, but it's a proposal. Even the authors recognize that, you know, it's a partial knowledge. it's incomplete. Not everything is known. The numbers that are there are tentative. Sometimes they don't come from humans, but from other organisms. And you know, you can barely see the fact that here there are nodes and edges. Is a huge graph. Every node is a metabolite. Every edge is a reaction. So how can you make a sense out of that? I mean, Alberto, my advisor, talked about skin the other day, and we were trying to do things with one variable, two variables. Okay, what about that? So if no, it's impressive, right? How when you measure yourself with biological systems, you feel this curse of dimensionality, this complexity that is amazing. If you want to adjust one variable for one of these nodes, even just writing down the system is overwhelming. So what can we do? Well, we can give up. Well, this is the first, right? Or we can say, well, let's get all the tools we know about and let's try to compose them. And I would use, I think, something, an idea that Roberto uses a lot of time. He talks about applied mathematicians as someone getting around with a toolbox, right? With a lot of different tools. And there is a problem, you try to adjust it. You are like a plumber with a lot of tools, you know, there is a leak, you try to do something. But you need a lot of tools, many of them. So just to mention this area of, for instance, metabolism or human metabolism, there has been many different proposals. Let me mention a few of them, like you can read a network flows approach, flux balance analysis, very famous among biologists, Markov chains, Laplacian dynamics, compartmental systems. And obviously this is just a little list. There are so many other approaches, just listed some of the other: zero deficiency theory, monotone system, network motifs, modularity. And again, this is just a selection. So the reality is so complex that there is not a unique mathematical model that will do the job. And there is no unique mathematical technique that will do that. You really need to compose to understand the problem, understand what you want to represent about the problem, about the system, and use all these different tools combined many times, and invent new tools that combine these tools, and so on and so forth. But the beauty is that once you have a mathematical formulation, then it becomes extremely powerful. As Ilaria and Massimo said, you can analyze, understand, and predict, and suggest way of controlling and modifying the system. So as soon as you give a network description with nodes and edges, you can ask yourself fundamental question like, okay, assume I know all the flows, so how the nodes interact. Can predict the equilibrium of the network in terms of the value of the nodes, or vice versa. I know the value of the nodes. Can I predict the flows that are compatible? And these are questions that are fundamental and has a lot of importance in applications. For instance, for human metabolism, like this very small network is the so-called reverse cholesterol transport, represent a very tiny piece of a much larger network, represent just the cholesterol metabolism. But you see, when you go and take a blood work, you measure some metabolites. But what about the fluxes, how they interact with each other? It's partially known. There are some theories, some experiment, some knowledge from model organisms, and so on and so forth, but there is a lot of unknown. So exploring even just the space of equilibria is fundamental. And let me show an example in which this was used. For instance, in collaboration with Sanofi, where we're trying to interpret a different effect of the statin-based drugs between men and women, and there were a significant difference. And depending on the menopausal status of women, there was also a significant difference. You see here, the colors are always, biased by culture, but anyway, there is a kind of light blue for men, and you see there was a better reduction of the bad cholesterol LDL compared to women that are indicated by reddish color. And it was not clear why this was happening, but it was definitely significant from data from clinical trials. So they had some idea of what could be behind. It's a subtle difference, but essentially estrogen interacts modifying PCSK9, that is one of the fundamental protein involved in cholesterol metabolism, and favoring transformation on another form called form X in the liver. Then when released to blood, they had a different effect on LDL. And how to explain that? Well, it's like a minor small modification that you are making of a very big network. And you know, having studied the equilibria allows you to modify your program, your simulator, and simulate again a different way and making it work. Because the reality is that some of these companies created this model, they do simulate, but the simulators is really ad hoc. You know, they just tweak here and there, they engineer the software, finally it produces a result. But as long as you change a little things here, you add an arrow, so on and so forth, everything blows up immediately. So by doing the mathematical analysis, you can produce tools that are much more stable and sort of produce more faithfully reality, because we are stable in the sense that we, as both Massimo and Roberto mentioned, we survive viruses, weather, many other things. So we have to be very stable. Our network must be very stable. Otherwise, we wouldn't be here. So using these tools that were based really more on the mathematical analysis and then trying to simulate, we were able indeed to have a very faithful, well, reasonably faithful matching of the clinical data. And so we validated the hypothesis that it was estrogen and the PCSK9 and X4 that was causing this difference between men and women. So you see, this is an example in which the mathematical approach and mindset is bringing this difference in the way you do things. So the power of models in explaining things that otherwise could not be explained. Let me make another example, the second last one, I promise. It's about, okay, let's talk about treatment. So tuberculosis is a terrible disease that apparently infected up to 1/3 of human population. Okay, 1/3. Not everyone develops the disease, fortunately, but among those that develop the disease, some need very strong cures. And these cures may be up to a combination of 4 antibiotics, up to 6 months. And some develop a resistance and need a second cycle. So if you have a bad form of tuberculosis, it's really serious and dangerous. By the way, it's now worldwide endemic. Means it's here, it's not going away unless we find something, some way of getting rid of it. So these are the type of data you have to deal with. Let me not spend too much time in formulas. I mean, I was not as good as Ilaria. There are some formulas here. I try to keep small. Anyway, here are a sample of available antibiotics on the market. Indeed, very established one. There are a plethora of new ones, more than 100. And these are the genes of the Mycobacterium tuberculosis. Before we were doing something good to the human, right? Now we want to do something bad to the bacterium. We want to kill it. So these colors that you see here, the lighter means that these antibiotics act strongly on this gene. And then you can organize the information in various ways. This, for example, is a map that is showing by the color correspond to the antibiotic. Here is just a list of genes. They are not organized because they interact with each other, just listed according to KEGS or other databases. And you see these dots is telling you, okay, this specific antibiotics is acting strongly on these genes. Then, as also Ilaria mentioned, you need to map the genes on the pathways and understand how these genes will affect the pathways by being up or down regulated by your antibiotics. And finally, you end up with maps of this type. This is, for instance, the biosynthesis of antibiotics. Now, it sounds like it's an antibiotic, it's not. So it's the pathway of the mycobacterium. The bacterium itself produces antibiotics as a way of protecting itself from the environment. And you see, you want to, for instance, disrupt this pathway and cause the death of the bacteria. And these maps are very informative. So here are all the reactions. And as you can see, many times the network is incomplete. Typical, we have partial knowledge. But here is a map, and you see on every reaction, we have colors like red for down regulation. Here is the name of the drug, or green for up regulation, or gray with a lot of names here because we have a lot of antibiotics, but some up and some down regulated. And so indeed, what happens is a well-known phenomenon in medicine that is a synergy or an antagonistic effect. Synergy means the antibiotics work together to do the same thing, in this case, to kill bacterium. When you see gray here, for instance, the antibiotic work in opposite ways. So when you combine them, the risk is that essentially they have a zero effect. So I will be very brief here, but you know, many times I hear this fact. I mean, I loved when San Giovanni Vincentelli said it's not useful now. It's not what was useless knowledge. It's not yet useful knowledge. That's the correct one. Because one thing we discovered in the last few years is that, okay, simple things, right? There is a network. Network is a graph. A graph is nodes are metabolites and arrows are connection. One metabolite favor the other produce. But even the simplest biochemical reaction you may imagine has a lot of reactant and a lot of products. So indeed, the very natural language is not the one of graph, but the one of hypergraphs, in which a single edge connects indeed multiple nodes to other multiple nodes. And if we think about enzyme and drugs, it's indeed that they act in this way. A drug could be an enhancer of a reaction. This means that there is the node, the drug, seen as metabolite, that acts over an edge. So indeed, you need what is called Uber edge, a theory that appeared in the last couple of years. So this just to say that don't worry whatever complicated math you are doing, it still is not going to be enough for the complexity of the biology system. So, you know, there is no level of complexity that will be useless for the future, by no means. Just to give an idea, you see, indeed, if you try to replace these natural hyper edges with simple edges, you are mystifying the dynamics. That's what you do. There is no way in which you can represent that complexity just with simple objects. You need really the level of complexity, math complexity, that is useful to explain this phenomenon. Again, this is the type of result. You see, you need to choose 4 antibiotics from more than 100. What's the combinatoric? It's 4 out of 100, so it's a huge number. Now, there are known facts like you never mix 2 injectables. There are antibiotics that are similar. So you reduce some cases, but this is a simple example of ranking all the possible combination of these antibiotics. And you can see that our method can rank, I don't know, if you see here colors, when you see, for instance, this color means that we are using moxifloxacin and so on and so forth. The rifampicin is green, you see it appear here a lot. This is a complete ranking of all the possible combinations that make sense with those antibiotics. And one can use these type of methods to make a first screening. You know, you discard what is really not working, you focus on what is working, and then you focus the clinical trial and experimental effort in areas that were guided by your computation. So it becomes really a driver, a facilitator of what is the biological investigation. I cannot end without thanking a lot of people, and obviously my large lab without a lot of people working with me. You see, these are the people at the time of Zoom. Without them, you know, I couldn't do any part of this work. There are an external collaborator that is even here in the room, and obviously the funders, like everyone, like Ilaria mentioned, National Science Foundation, DOE, NIH, Department of Transportation, and the private companies, Critical Path Institute, Sanofi, Excella, Bill and Melinda Gates Medical Research Institute. Last but not least, you know, in life we are not only mathematicians, we are also people. And here there are 2 friends of mine, Stefania and Michelino. So thank you so much for being here, and obviously to all of you for listening to us.
Okay, so now we can go to the second part of this table, even if you used quite a lot of time, but anyway. The second part is to ask you, now we don't need more, maybe you have some slides. One, just so that's now that's ready. Okay, so the second part of this table is to ask, our speaker a bit about their motivations, their way to mathematics, why they choose this kind of problems. So, so first of all, while Massimo is working on his computer, I asked to Ilaria if why you choose to do mathematics, and especially why you study epidemiology, why you are interested in this kind of difficult problem where you are not just alone with your mathematics, but you need to interact with the real world, and so that's a challenge anyway for a scientist.
Yeah, so it's a good question, and I did maths at the university. I did maths at the university because I liked it, and just what I wanted to do without thinking what I would go and do afterwards. Like I had no idea what kind of profession I would do, but I had the support of my parents, and so I just thought I'd do it because I like it. And I discovered that there was this field of mathematics applied, to epidemics. Like it was called biomathematics in my university, that course. It kind of blew my mind. And if I have to look within me, that's because perhaps I had my secret dream about studying medicine, but just for how I am, I think I wouldn't have been very good at being a doctor. And so it's like I found a way of combining the two things, you see? So I have my passion on the maths, and I had my secret dream of doing medicine. And in this way, I combine the two things. And I must say, I love interacting with people who do work on diseases, but they come from different fields. And this is something I have to do quite often. It is challenging because we speak different languages. So they use different terms. Sometimes it's quite difficult to understand each other, but sometimes it's just a matter of understanding how different the same thing is called different. Sometimes it's just, just having those keywords that really allow you to see, okay, we are in sync. I can understand what you say. I can understand what you want to do. I need to simplify often what you want to do, but I can do it. And so this is very interesting, I think, to see how we can, kind of combine different disciplines. And at the end of the day, I love what I do because I think I have a purpose. I use maths in the interest of health, which is one of the best things that we have. I think we need to protect our health. Of rich countries, but also like globally. It's not just us in the world, it's also like global health, global south. And I don't know, this is my purpose. I think I'm doing something good for society by using these tools, trying to control epidemics.
Okay, thank you very much for your now I'd like to inverse because I want to finish with Massimo. Benedetto, why have you started mathematics? It's not completely obvious, maybe. You could choose other things. And in particular, you have a very singular path in your career because you started with the control theory, which is quite classical in mathematics anyway, on the border of engineering in some sense. But I mean, it's anyway a well-established field. And you went very far outside of standard topics. So why this kind of way?
So thank you for the question because it's great. But I think that it's I like it really what Ilaria said, that what drives us is mainly passion, interest, and doing the good. And then usually, the path is bumpy. You just bump here and there. What I can tell you is that I was in high school when I was extremely passionate about the history of the solar system. So with obviously Ptolemaic system, then Copernicus, I spent some time here in Padova, Galileo that taught here in Padova. And so I was trying to understand this system. And then I was working with my brother at building computers and writing programs. So I write a little programs to simulate the different model, going all the way from Ptolemaic Tycho Brahe model was amazing, and so on and so forth, coming all the way to the Copernican one. And I think that I had one of those moments, and then I was simulating, taping, and so on. One of those moments in which you say, well, you mix everything together, right? There is the history, there is the science, there is the mathematics, the computer programming, and I think that I really love doing that. So trying to do the activity when these things are brought together. And then a lot of accidents. So the first accident was in high school, my math teacher, don't tell her, was not that good. And so, you know, I was convinced I had to go and do astronomy. Then my father, who was professor here at the University of Padua, paleontology, sent me to talk to an astronomer. And I have to thank him because he scared me to death. And he said, forget about that. You will never do anything and so on. So I decided to do math. Then I started to do math, but at the same time, I was still working with my brother, doing a lot of programming software. And then the accident, Padua professors that were so good that dragged me into math. I mean, I could not stop doing it. So I said to my brother, sorry, you have to do math. And obviously he became a rich man and I became a happy man. Not that he is not happy, not that he's not happy, but I'm definitely happy. And then a series of accidents, like I was so lucky to get as advisor Alberto Bressan. They happened to be the brother of my course mate, Sarah. So again, a chance. And then why I did many different fields? Well, also because of Alberto. Alberto is doing 10 things at the same time, so I have to imitate, you know. But then at the same time, I'm more applied than Alberto, can I say it? So I really liked to work with applications and going back to that moment of mixing the things together. So little by little, I started to work more with a lot of different people, and language. Oh my, is number one, especially because of oh my, because as mathematician, we always think in a bijective way between names and objects. So a graph is a collection of nodes and vertices. You go to engineers, physicists, physicians, biologists, and so on. They don't have that. So they give you a name and you are convinced it means something. And then after a week, it means something else and you are lost. So establishing a language is really number one, fundamental to even just start thinking about that. Anything.
I'd like to finish with this kind of second tour of the roundtable by asking a bit different question to Massimo. Massimo, you told me that you like to solve impossible problems, and maybe you want to mention, so you have this picture, what your first impossible problem, maybe many more you solved in your life, and you will solve in the future. But maybe you can tell to this our audience what's your first impossible problem.
Well, I thank you very much for this question because it gives me the opportunity to tell a small story. So, yes, right. Sorry. Well, when I was finishing my studies at this university, I was pretty quick, and I searched for a thesis. And at the beginning, somehow, some of the professors to whom I asked the thesis, they told me, well, you know, I have to think about what topic I would like to give you. It will take some time, I have other students and things like that. So I saw myself having some buffer of a couple of months or 2 months in front of me. And I was somehow feeling very anxious. I mean, I was running fast and then wanted to do the next thing, right? So, and it happened by a chance that I got to know that there was a professor in physics at the Department of Physics, Galilei here. And that was having an idea of working on image processing. I mean, that was kind of it sounded very attractive. And And so I asked an appointment to this person, and I went to the office, and I said, well, you know, I have some time, and I'm very eager to stuff. And so they told me that you're working on an interesting problem, and then he mentioned to me that somehow he was indeed working on an interesting problem that was about restoring a fresco. And well, I was very impressed by this, and I tried to understand what it was about. And it was about some frescoes that belong to a church here in Padova. Some of you maybe from Padova know this church is the Remitani Church, with the Remitani Museum. And this church was destroyed during the Second World War. It is part of it, right? And inside this church, there were some frescoes, and in this happening of the destruction, the people in Padova collected all these fragments, or many of them, and more than 100,000 of them. And somehow they, well, sorry, I have to. Yeah, 100,000 of these frescoes, of these fragments. And the problem was to basically repuzzle up this fresco. I mean, I guess that many of you have done some puzzles, like 5,000 pieces, 10,000 pieces, something like that. Well, this was more than 100,000 pieces to be repuzzled back. Plus, the fresco was, the puzzle was incomplete. Many of these parts of these frescoes were not anymore available, and so it was an amazing problem. And I asked him whether I could collaborate, and he said, "Well, I don't know." He was very, very cautious, as many professors are with respect to some very young student. And then I showed him my libretto, that was the booklet where we had all these marks. And I wanted to impress him with my best marks, right? And then when he saw the marks, he got scared. He said, "No, I don't want such a good student, because then he may expect a lot out of it, right? So I don't want anybody that has too high expectations." And so that's something that he told me many years later, that actually he thought that. But and so I saw his hesitation, and I asked him, "But exactly what are you planning to do?" And then he started to explain to me a little bit the ideas that he had about using a certain kind of Fourier analysis to try to apply to these images, to try to find a way to compare images independently of rotations. And then I started to think, well, that's mathematics. That's something I can do. And then I told him, "Well, you know, I have 3 months. I will bring you the results in 3 months." You know, and then when I promised to him such a thing, he looked at me and said, "Well, I will not pay you until you have done it," right? So because he had some little fundings for that, and he could give some scholarship, and we agreed on that. I agreed that I won't be paid without the results, and so I started to work on that. And by working on that, I started to be hooked on that. And well, to make the story short, we did an amazing experience together at the beginning, because somehow at some point our ideas were working, and at some point we started to see that we could find the fragments in the original positions on some of the pictures of this, some photos of these frescoes dated to the 1920. And we went to the Fondazione Cassa di Risparmio of Padova e Rovigo, that is a foundation here. We asked them at that time really a lot of money, and they gave us this money, and eventually we built up a lab. We basically repuzzled through the work that we've done in the lab, the entire fresco, and eventually in 2006 it started the restoration. And now if you go to the Church of the Remitani, you can see the frescoes back within the walls of the Cappello Vetari. And somehow this was one of amazing experience that I did at the very beginning of my path that determined very much my way of working. And I owe a lot to the professor in physics that introduced me to his way of thinking and his creative point of view. and that embraced as well as somehow Benedetto embraced a little bit the attitude of his mentor. And I have to thank him very much. Unfortunately, he left us only a few days ago. And so, yeah, that's my story about that. Right.
Maybe now we have just a few minutes, I think. Yeah. But maybe we have time for 1 or 2 questions from the audience. So if you want to ask your question to our speaker, that's the moment, but very short. And also the reply has to be short. Some curiosity, even a young student for your future career, if you want some advice, I don't know. You're so shy. No. Maybe the organizer.
I have a question.
Okay. That's not prepared.
I'm sorry. Thank you very much. We planned this round table, and it has been exactly as awesome as we thought. So thank you very much to the 3 and 4 of you. But the question is, you talk a lot about connection with other parts of science or medicine or whatever. Is it something that university helps connection with other topics are not very easy, and I'm not sure our universities help us on that, help our students. They kind of force us as teachers and their students, and the PhD students in particular, to focus on our topic, and that's all. Then I have been lucky, like you have been lucky, you have mentors that open your mind, but the system is, especially here in Italy, very closed. Can you maybe give us some advices on how to make this connection, how to deal with other people that speak a different language, for example? Thank you.
If we have people.
That's a difficult one.
Oh, what?
Yeah, I don't know. That's a difficult question. I think in the sense that I don't know if I'm the best person to answer this, because effectively I am working in the Faculty of Medicine. So, you know, I am a mathematician by background, but at the moment, I'm not really in a mathematical department. So I am really surrounded by people who are not mathematicians, but I have many people like with similar kind of background, physicists, you know, so very technical. But we live in an environment where there is very much a mix of, you know, different sciences coming together, and that's helping us a lot, I think, kind of merging and sharing. So often you discover that actually, you know, there are differences, but there are also many similarities in the way we approach problems. And yeah, so I don't know, I mean, from my perspective, so how we work is we build models around data. So we have problems, and typically for me are public health problems. We have very real questions that we want to answer, and then the model and the modeling and the tool comes after. So, you know, I'm not picky in the sense that I use whatever needs to be used in order to answer the question. It can be statistics, it can be the standard compartmental model, it can be machine learning. So you need to be able to adapt, you need to be willing to learn a bit and to go outside your comfort zone. But yeah, I don't know, my objective is answering the question in, you know, and even if I go maybe beyond what is my confidence, I'm always want to be mindful in the sense of, you know, there is a scientific method. We need to be sure what we say. We need to validate our models. We need to avoid the identifiability issues, this kind of grounds, you know, and pillars in the way that we have been trained that we need to keep and maintain, because effectively, you know, when you work on medical sciences, you have that kind of responsibility on yourself. You're not doing toy models only, you're even advising, you know, governments or use of medicines. So you want to be sure and as sure as you can, you know, about what you say. So, you know, there is lots of cross checks that you need to do before, you know, you just say anything.
Okay, thank you. I think that it's kind of, in one word, that you're saying that you have to stay open, and maybe you have to contact this kind of metaphor that for a man with a hammer, anything is a clue. But here we need a big toolbox to distinguish the different problems, and so to attack with the right tool the specific problem. So that's maybe the secret what you're saying.
So if I can now answer more from the institutional point of view, that I think was also part of Francesco's question. I mean, this has been an everlasting debate, right? These lower barriers and cross-discipline and so on. On one side, it's obvious, I mean, human knowledge specifies so much that becomes more and more difficult. But on the other side, at least at the level of United States, at least more my experience, the new calls of the National Science Foundation, they all speak the same language. Lower those barriers, do cross-disciplinary investigation. I submitted now a grant in which there is myself, a structural bioinformatician who is a physicist, a psychologist that is expert of social determinants of health, an expert of public health, a social worker, and a sociologist. So I think that that's what the push is going. And US is oftentimes, you know, ahead of the game in some areas. But you see, indeed, Francesco, the meeting that you organized here, it's a great example. Because also in the first 2 days, we had from Claire Wazen to Jan LeCourne, from Alberto San Giovanni Vincentelli, to Laura DeMarco, and so on and so forth, to historian and so on. So I think that the future is in that direction. If you decide to be very interdisciplinary and stay in academia, some barriers will be there, but the future belongs to this mindset.
If Massimo wants to add some final words.
Well, my point of view about this is that yeah, well, you can work in one direction and get deep on that. That's one way to do that. But you can also, in a certain sense, try to connect things, right? That's another way to do. That's, for instance, the way I decided to go, because it's the way I have most fun, seeing connections between things that are kind of different. They look different, but then I show that they are not. Yeah. That's the fun for my research, and I think that there should be more space, even within mathematics, for the mathematics of connections. For instance, there are some problems in mathematics that cannot be solved by deterministic arguments. The Cauchy-Schwarz inequality, it's a bad inequality. You lose a lot. Even the triangle inequality, it's a bad inequality. But if you write the same thing, the same quantity in a probabilistic sense, all of a sudden you can choose the inequality. You have to pay a price. Maybe you have to pay the fact that that inequality will hold only with high probability or with some probability. But all of a sudden you can write completely new tons of theorems that have an hypothesis, a statement, and they conclude by the sentence with high probability. So which means that you have some truth, right? Maybe it's not the typical truth that mathematicians are often taught to search for, right? Deterministic truth, but eventually it's a great theorem because it tells you this is how things work most of the time. And amazingly, you can do a huge amount of things, but then you have to connect mathematics from probability with other fields like analysis or with algorithms, for instance, right? So this is an important lesson. I believe that even within mathematics, it's acceptable, yeah, because there are some people that are good in that, like connecting things, right? At the same time, you can have really new mathematics coming out of it. So that's my hope, that there will be more room and not. I liked very much the metaphor that Ingrid Obeshi used. It's beautiful to think that we have to learn to ride a bike. That has a lot of degrees of freedom, and it's allowing us to keep balanced. And the fact that we have more room for moving allow us to go straight, right? But if you get into somehow some tracks with your bike, sometimes you get stuck or even fall, right? So I really like that metaphor, and I think it also in the terms of the interdisciplinarity.
Great. Thank you very much. We'll finish now our table, because also I think the organizer become nervous. You know, that we have to exit from the room, from the building maybe, and so on. So thank you very much again to the first to the organizer, even if they are nervous, the University of Padova, Unione Matematica Italiana, and to our speakers. I think that today we honored the memory of Vito Volterra. So I thank Enrico Volterra to be here today with us. And okay, I hope for, at least for young people, it was useful to listen to this experience. Thank you very much. Anche per i più vecchi, era utile per tutti, lo so, per i